The unit 4, we want to make sure you can write the chemical formulas. You can name if the formula is given, you name it. If you have the formula, you write the name. You have the name, you write the formula for ionic compound and for molecular compound. And then some properties for my ionic compound, properties for molecular compounds. So if you have a binary ionic compound, how would you name it? Okay. So if the formula is given to you, you are going to identify the first element. You have access to periodic table. So you know that this is a beryllium. Okay. And then you identify the second one. You give the root name for the second element. This is for binary ionic compound. What does binary means? It means that it's made of only 2 types of elements. And if it's ionic, means that it's coming from metal and non-metal. So you give the name for the first, for the metal. Metal in ionic compound, metal is written first, non-metal is written second. And you always have empirical formula. That means the lowest whole number ratio. And if for some reason you see numbers that they are not simplified and purpose, that means that you're dealing like for peroxide something. So for example, Na2O2 is ionic compound, okay? And you might say, why this should have been, this something is wrong, but instead of finding something is wrong, think about or find what is this compound. Actually, the name of this is, this ion is an O22 minus and is not oxide. That ion is a peroxide. So if you see those numbers not simplified in ionic compound, there is a reason for it. Because if they give you formula for ionic compound, it must be simplified. Because the charge of oxygen is a -2, the charge of beryllium is +2. When you actually write the formula, it goes to 2 and 2, and then it's simplified to BeO. So when you are naming it, you would just say the name of the first one, beryllium, root name for the second one, which is ox, okay, root name, and then add IDE. So you have beryllium oxide, you have aluminum chloride, you have sodium bromide, aluminum chloride, potassium oxide. You notice I don't care about these numbers, okay? Because it's understood that if you have 2 oxygen, you must have 1 oxygen, you must have 2 potassium to cancel the charges. Okay, so if the formula is given, that's how you write the name for ionic compounds, binary ionic compound. Now, if your compound is higher order, that means you have more than 2 types of elements, or another way of saying is that if you have like polyatomic ions involved. So first of all, you have the name for these polyatomic ions. We did some examples of this last, but I just want to make sure that it's covered again to make sure that you have them in the record, in the PowerPoint. You want to first of all, if the formula is given, okay, so if the formula is given and is NH4 3 phosphite, NH3 okay, ammonium and phosphite. So if it's 2 polyatomic ion, you go to the table for the polyatomic ion that you have memorized. Ammonium is +1, and the name of it is ammonium, and then a PO3 is a phosphite, and it's not a phosphate, it's a phosphite. So you just give the name of the first polyatomic ion and second polyatomic ion. again, these numbers, they are understood that if you have one phosphite with the 3 minus, you must use 3 of the ammonium ion with the 1 plus charge each. So this 3 is to satisfy the charges for the other components. So if you are given like a formula like this, to name it, what you need to find is this is the polyatomic ion in the periodic table. I'm sorry, in this table for the name of the polyatomic ion, we know that it's a sulfate. And then you bring the name of the metal first and then say the name of the polyatomic ion second. So sodium sulfate, ammonium phosphate. Sodium sulfite, here it should have Na2SO3, is a typo, I corrected. And then ammonium phosphite. Someone had a question. Let me hear the question again.
Yes. So which reference should we use to memorize the polyatomic ions? Because I'm seeing more polyatomic ions in this diagram than the diagram that you had last class.
Okay. Unit 4 covers the naming, basically.
Right,
and since
okay.
Unit 4 is, so try this one. Okay.
So memorize this diagram.
Yes.
Okay. All right.
Okay. So if his ionic compound, if it's a binary or if it's polyatomic ion, you bring the name of the metal first and then the other side. If it's a binary, it would end with IDE. Okay, that's for binary. So we know that if you see IDE, with exceptions to just the hydroxide, it's going to be, and cyanide, those are the only exceptions. Binary, that means it's made of only 2 types of elements, AX, BY, that is binary. The name ends with IDE. For polyatomic ion, except for hydroxide and cyanide, everything else ends with either ATE or ITE, ATE or ITE, except for hydroxide and cyanide. Okay, these 2 are IDE, and you just have to remember that they are polyatomic ion and they are not binary compounds. So if you have a sodium hydroxide, it's not a binary compound. You have more than 2, but it's understood because it's hydroxide, or for cyanide. If you have ionic compounds containing elements from transition metals, often transition metals, they have multiple charges. And for the multiple charges, you want to know about, memorize iron with the 2 and 3, copper 1 and 2, lead 2 and 4, and then tin 2 and 4. Others will be given, like we have also for gold, we have 1 and 2, silver is always 1. So these 4 memorize the variable charges. So if you have these compounds, if the formula is given and you're writing the name, you must indicate what's the charge of the, what is the charge for transition metal that you have. So in order to write that, you would use a Roman numeral, and then you indicate the charge of the plus 1, the cation or the metal. So in this case, you have charge for FeCl2 is iron 2 chloride. Now, how would you identify it? because that's the key. If you know it already, you know it. How would you identify the Fe is 2 plus? Then you look at the counterpart. The counterpart here is Cl. Cl is chloride. We learned that in previous chapter. Chloride is 1 minus. And since it was required to use 2 chloride in order to cancel the charge of the iron must have been 2 plus. Or you could say, let me do reverse. Let me reverse it. I'm going to give this to the iron, the 3 from chlorine to iron, and the 1 from iron to chlorine. So chlorine is a 1 minus and the Fe is 3 plus. It works often, but you just have to pay attention to the like making sense, and if it doesn't, if it doesn't make sense. Like if you have a FeO, if you give 1 and 1 back here, then you say, okay, charge of iron is 1. That's not true because oxygen cannot be 1 minus. Oxygen is 2 minus unless it's in peroxide. So it's a 2 minus. So this must be 2 minus. So you can use this general shortcuts, but pay attention to common sense. Make sure that it does make sense. So the formula for copper 2 sulfide, if we say copper 2 sulfide, so we know that is a copper 2 plus, and then sulfide is a 2 minus. When you combine and simplify, you come up with CuS. Name for FeSO4, how do we know this is a iron 2 and not iron 3? Because the charge for SO4 is a 2 minus, and we have that in the table for the polyatomic ion. SO4 is a 2 minus, so this must be 2 plus, and that's why you are using iron 2. Your question. Did I answer your question?
So we don't necessarily have to memorize the chart. We just have to look at the other atom or other element and determine what is needed from that element.
Yes. That's the only way, because if they say if you get like a FeCl3 and you get FeCl2, the only way you can find the charge for this is the charge for the other. Okay? But knowing that you have like Fe2 and Fe3 plus, and memorizing these is basically, it's not hard as long as you don't think that iron is 2 and 4, just like lead and tin, because most of them are like 2 and 4, and then iron is 2 and 3. Okay, that's for naming for compounds that contain transition metals. Naming of acid. Acid depends on your acid. If it's a binary acid, again, if it's a binary acid, that means you have only 2 types of element, HCl, HBr, H2S. These are binary acids. Okay, binary acid, the name ends with IDE, right? The name of this: hydrogen chloride, hydrogen bromide, hydrogen sulfide. The acid name is going to start with hydro, and then the root name for the non-metal, and then ic acid. So you would use the hydro and then ic acid, hydrochloric acid, hydrobromic acid, hydrosulfuric acid. Okay. So you start with hydro and then end with ic acid. This is for binary acid, meaning hydrogen and one other element. It doesn't have any oxygen. If you have an acid with the oxygen, let's say you have H2SO4, then you have to look at the name for H2SO4. If this is an ATE ending, this ion is AT ending. So for the acid name, no hydro. You don't use hydro, no hydro, because it's oxyacid. For oxyacid, as we have it up here, for oxyacid, you look at the ending for the name of the anion or the oxyion that you have there. If it ends with ATE, then you would use ic acid. Root name for the sulfuric acid. So root name for the polyatomic ion, and then add ic acid. Phosphoric acid or sulfuric acid. When do you use OUS? OUS acid is, you would use it if you have polyatomic ion that ends with ITE ending. If it's ITE ending, then this is going to end with OUS acid. Sulfurous acid, nitrous acid, so HNO2 is going to be nitrous acid. And so nitrous acid or sulfurous acid. Root name of the polyatomic ion and OUS acid. When do we bring the OUS acid? I'm repeating, is if you have ITE ending. Okay, since we talked about the acids, I also want to talk about the base, because if this is a general chemistry, is like core chemistry for your majors. For the base, what is classified as a base is the hydroxide of a metal is base, okay? That's a base. Calcium hydroxide, CaOH2 is base. So if you see hydroxide and metal, that's base. You know, is a base because is a metal hydroxide, and that's for group 1 and 2. Group 1 and 2 hydroxides are base. So when you name it, you just say metal and then hydroxide, sodium hydroxide, calcium hydroxide. You don't have to be worried about 2 or 3 or others, because we know that hydroxide is 1- and calcium is a 2+, so you must use 2 of the hydroxides. Molecular compounds. I don't know how many of these I have. I just want to make sure that I have time to cover. Molecular compounds, for naming molecular compounds, you have to be worried about prefixes, and you are using the prefixes di, tri, and penta to show how many of each you have, because you could have variable subscripts. Like you could have nitrogen with one nitrogen, 1 oxygen. You could have 2 nitrogen with 1 oxygen. You could have 2 nitrogen with 3 oxygen. You could have more. Okay. So because these combinations are allowed and is not always the empirical formula, even if it's like N2O4, you have to, or NO2, you have to, these are all possible compounds for combination of nitrogen oxygen. So the two compound cannot have same name. So if it's, you cannot say nitrogen oxide and nitrogen oxide. This is like dinitrogen tetroxide, nitrogen dioxide. If you're using, if one element for the first non-metal, you don't have to say mono. Okay? Now, if the name is given and you want to write the formula, then you are going to find what are the elements. You know that we have phosphorus and oxygen. It's phosphorus and oxygen, and ID ending is just the two types of the elements that you have in there. How many phosphorus you have? 4, and how many oxide you have is 10. So you would write the one with the lower electronegativity. In ionic compound, you write the metal first. In molecular compound, you write the one on the left side, or the one that is closer to metals first. Phosphorus, it can go either up, down, or it can go to the left side for the more metallic property. Phosphorus is more metallic than oxygen, has lower electronegativity, so phosphorus should go first and then oxygen. And that's not it. How many phosphorus is 4, and how many oxygen is 10. For sulfur dioxide, we know that sulfur is less electronegativity than oxygen, so sulfur should come in first, oxygen should come in last. How many sulfur? It doesn't say, so that means that it should have been 1, oxygen 2. You wish everything was this simple, right? Okay, what is electronegativity? Electronegativity, the term of electronegativity is applied to covalent bond, which is the bond between two non-metals. So when you say electronegativity and you have a bond between hydrogen and chlorine, the desire or tendency to accept this pair of shared electron by chlorine is determined by the electronegativity. So chlorine has higher electronegativity than hydrogen. So electrons have negative charge. So this means if you were showing these lines or dots as the electron cloud would be more dense around chlorine than around hydrogen. And that means that we can give like this symbol of delta negative for chlorine because it's negatively charged, and delta positive for hydrogen that is positively charged. The electron distribution is not even. So we have more electrons around chlorine, less electron around hydrogen. It's not even. This bond is called a polar bond as well. So electronegativity is like how much they like to have the electrons. It was, these numbers are not like a measurement, basically, it's just a comparison. Fluorine has the highest, and that is a 4.0, and everything else is compared to the fluorine. The numbers are between 0 and 4, and that's what we have these numbers. These numbers represents the electronegativity. When do we use it? When we want to know if the bond that we have is polar or is not polar. Electroaffinity was the amount of energy that was released, but electronegativity is just a comparison to fluorine. If you have a bond, you have the values for electronegativity. You can say those electronegativity, like which one, if is the bond polar or non-polar. In order to decide that, you find the difference in electronegativity. Delta stands for change, and En is electronegativity. If the electronegativity is 0, that means the bond is non-polar, regardless of what the electronegativity is for chlorine. And since it's the same, the overall is going to be 0. So if you have a Cl2, this bond is non-polar. Same thing for H2, the bond is non-polar. F2, I2. And then, but if you have electronegativity difference, like for HCl, the difference in electronegativity is 0.9, and that's higher than the 0.4, it is polar bond. If the difference in electronegativity is more than 0.4, is going to be polar. Okay, the difference in electronegativity, if is greater than 0.4, is polar. If it's between 0 and 0.4 is non-polar, And if it is more than 1.7, is going to be ionic. So for NaCl, because is okay. I hope that you don't tell me you don't see the okay, you see it. I had to double check the screen that I'm sharing. I'm sure you would have told me something, but just want to make sure. So if the difference is more than 1.7 in some books, other books for simplicity, they use like 0.4 and 2, the cutoff line. If it's greater than 2 is going to be ionic. Say that if it's greater than 1.7 is ionic. Your book, it says between 0.4 and 1.7. We can use that as your reference, okay, for your calculation. Difference in electronegativity. Some compounds, they have polar bond, ionic bond, and covalent bonding. That's like KNO3, the bond between nitrogen and oxygen is covalent, but a bond between potassium and nitrate ion is ionic. So just that also to add to what you had before. And how strong is a bond? Why we talk about the strength of the bond? What does it mean that the bond is strong? When it comes to Na plus and Cl minus, the ionic bonding, this bond is the attraction between positive and negative charge. And if you want to separate this, you have to spend energy and cut this bond. When it comes to ClCl, is a covalent bonding. So you have a plus charge, and then you have electrons here. This plus charge is going to basically attract this shared electron, and the plus charge from chlorine also attracts the pair of electrons. So both of them are attracting the same electrons. So there is the attraction force here from the nucleus to the shared electron, nucleus to the shared electron. And if you were going to break this bond, you have to spend energy. The stronger the energy, the bond is, more energy you have to spend. Bond, when it's forming in general, when the bond forms, you have to, the energy is going to be released. That's known as a bond formation energy. If you break a bond, you have to spend energy. Like what is happening in this reaction, you are breaking 4 bonds. You're breaking this bond, this bond, this bond, that bond, because you're going with carbon and 4 hydrogen. The sign for delta H is positive. What does it mean? It means it's endothermic. You have to give energy to break this bond. If you divide this, because they are all the same, by 4, then you can find the value for 1 CH bond. So you divide that by 4, and that's what is given here as 415 kilojoule to break 1 CH bond. Okay? So we have the bond formation, bond dissociation. Bond formation, energy is released. Questions?
Yeah. Will the electronegativity for each atom be reflected on the periodic table that is given to us during the test?
No, maybe not, but it will be given. You don't have to memorize it. You just have to know that if it's a metal, non-metal, it's ionic. That's like there is no need to give you the values. If it's 2 same non-metal, is going to be pure covalent, is non-polar. If it's 2 different non-metal, you can assume that as polar. If the question gives you the values for electronegativity, you do the math. That was a good question, actually. So if it's 2 non-metal, same non-metal, it would be non-polar. 2 different non-metal would be polar. Metal with non-metal would be ionic. And 2 metals, they never form bond together. 2 metals, no bond formation. The amount of the energy being released in a reaction can be calculated based on how much energy was consumed to break bonds and how much energy was released when the new bond formed. Okay, like here, you break one pi bond here only, and then you get a hydrogen bond, CH bond, and then you get the COH bond. So you have to see how much energy was released based on the amount of energy being released per bond forming and how much energy was consumed based on the number of bonds that they were broken. So if more energy is released, as a result, we know that it's going to be exothermic. If more energy is being consumed, then it means that it's endothermic. The value for bond energy will be given to you. The only thing is for you to find out is like to be able to count how many bonds are forming and how many bonds, or which ones are forming and which ones are the bonds that are broken. Like in this reaction, the first reaction that we have here, what are the bonds that are broken? Is a hydrogen-hydrogen bond. The value for this bond will be given to you. And the Cl-Cl is broken as well. But you're getting 2 HCl bond that is forming. So if 2 HCl bond is forming, this amount of energy would be released. And then you add these two values together. That's the amount of the energy that is being consumed. So product and reactant. So if you do the reactant minus the product, and the overall value is, you add all bonds that are broken for reactant on the reactant side, and all bonds that are forming on product side. And you say the bonds broken minus bonds formed, all bonds formed. If the value is negative, overall value, that means is exothermic reaction. And if the value is positive, it would be endothermic reaction. I already talked about these pure and polar. Like this is pure non-polar, but HCl in this case is a polar because you have two different non-metal. You can also find the electronegativity if the electronegativity is given. If not, just use the general trend. The one that has higher electronegativity gets the delta minus. The one with the lower electronegativity gets the delta plus. Formal charge and the answer to your question about the Lewis structure. To draw Lewis structure, I'm going to draw Lewis structure for NO2, and I'm going to start from scratch to find the, or let me do SO2 first, because I want to also talk about the resonance. Okay. So SO2. The backbone of the molecule, the one with the lower electronegativity is going to be in the center. And then we have the oxygens on the side. And now, count how many valence electrons you have. So you need the total valence electrons first, total valence electrons. I have, from sulfur, I have 6 valence electrons. From oxygen, each one has 6 valence electrons, so that would be 2 times 6 valence electron. If I add these two together, I have 18 valence electrons to begin with. Did you follow me so far? So you get the molecular formula, you draw the backbone of the molecule based on the lower electronegativity would go in the center, and then the one with the higher electronegativity, they go to the side, because the one with higher electronegativity, they don't want to share too many electrons, they don't want to go to the center. So if you have SO2, S goes to the center, O would go to the side. Count, these are steps, please write it down. Count how many valence electrons first, okay, total. I have 18. Step 2, use electron, connect, okay, connect them. I use simple terms, connect them. Connect and subtract. What should I subtract? How many electrons did I use to connect? I had 18 electrons to begin with. I had 18 electrons. Now I used 4 electrons, right, to connect, because each dashed line is 2 electrons. If I use 4 electrons to connect, now I have only 14 electrons left. With the 14 electrons that I have left, I have to satisfy the side elements first. So then give electrons to side atoms. Is not called side atoms. The technical term is like domain elements. Okay, I say side atom to make it simple. Then you would give, how many electrons should I give to this oxygen? I'm going to call this oxygen 1 and oxygen 2. How many electrons should I give to oxygen 1?
6.
6, because it's already has 2 electrons. So I'm giving 6 more electrons to make it 8. How many electrons do I give to oxygen 2?
6.
6 also. So after I say give electrons to the side atoms, then I should say and subtract. How many should I subtract here? $12 electrons. Why did I subtract 12 electrons? Because I gave 6 to oxygen 1 and 6 to oxygen 2. How many is left? 2 electrons. What should I do for that? Give the remaining to central.
Yeah, lone pair.
So as a lone pair, perfect. As pair. Okay, you give them as pair. Since you only have 1 pair, you give 1 pair. Next step, make sure that every element has 8 electrons. We already made sure that the center, the domain, the oxygens, they have 8 electrons. Now, if central atom doesn't have 8 electrons, is missing electron, what you do, you start sharing more than 1 pair. Additional sharing. Use additional sharing. Okay, so how many electrons do I have for oxygen 1? Total.
8.
8. And for oxygen 2, I have 8 because they are identical, but the number of electrons for sulfur is only 6. I cannot bring electron from outside. 6 is not acceptable for sulfur. So it's going to have, what's going to happen, we bring 2 electrons, as you have to share them as a pair, okay? Sharing as pair of electron. So you bring 2 electrons from 1 oxygen, either one, okay, to the center, and then you start sharing the second, okay, your second pair. So you have to remove that from the oxygen. You cannot double dip. You cannot keep it and share. When you're sharing, you have to bring to the center and share. Now, count the electrons for sulfur is 8 electrons. You count the electrons for oxygen 1 is 8 electrons, and you count the electrons for oxygen 2 is 8 electrons. Now we have a Lewis structure. Okay, so that's how you get your Lewis structure. Now, I said I want to talk about the resonance as well. Okay, in order to talk about resonance, I can say which other element can share electron with sulfur other than oxygen 2? Can oxygen 1 also share electron with sulfur? And if oxygen 1 shares electron, would sulfur be satisfied? So these two, okay, now if I look at these, I have 8 electron for sulfur, 8 electron for oxygen 1, and 8 electron for oxygen 2. So both of them are acceptable and they are very similar. It's kind of identical. Because in either one oxygen has double bond, one oxygen has single bond, and sulfur has one double bond and one single bond, one pair of unshared electrons. The two structure with respect to each other, they are called resonance. When you are drawing resonance, you cannot change the location of the atoms. So the nucleus stays there. Pair of unshared electron can change, pi bond can change. So you have pair of resonance. Now, when you have more than one resonances, that's basically this slide is talking about. You can find the number of, you can find the formal charges. And when you find the formal charges can be like, when you are determining the formal charges, the lower, if you have more than one structure, that means you have 2 or 3 resonances, the resonance with the lowest formal charge overall is preferred, is more stable, because we don't want like charge distribution or too much charges. If you have like a 0 formal charge, that's preferred. If you have lower this like difference in the formal charges, that's also preferred. So what makes the structure for N2O on the left side better than the one on the right side is that, to back up these rules, you have oxygen that has 0, and then the 2 nitrogens, you have a +1 and a -1. In the one in the other structure, you have oxygen that has a +2, and then you have everything has formal charge. So there are 2 advantages to the structure on the left, because you have one with the 0, okay, one with the 0, and then you have charge distribution is or separation, charge difference is less significant here. You have a +1, -1. Here you have a +2. The other big problem, there's a big problem here. Oxygen is taking plus charge here. That's not good. Oxygen cannot take plus charge because oxygen has higher electronegativity compared to nitrogen. So this is not a good structure, because oxygen cannot take positive charge. It's not going to make the molecule stable. Now, to count or to calculate formal charges, how do we calculate formal charges? The steps are given here, and we can calculate the formal charge. It's basically the difference between the electrons, the number of electrons that belong to the atom in this molecule compared to the atom sitting in the periodic table. So in order to calculate formal charge, you start with how many, I'm going to call this oxygen 1 and oxygen 2, and I'm going to call this structure A for sulfur dioxide, and I'm talking about structure A, sulfur dioxide here, A, and I'm trying to find the formal charge for sulfur. The formal charge for sulfur, formal charge, okay, is valence electron for sulfur, it's 6. How do we know that? You're 1045 students now, you know that already. You go to periodic table, group 6, everything in group 6A has valence electron number of 6, minus Number of unshared electrons. How many unshared electrons I have for sulfur? Answer so I can move on. Please, how many? For sulfur, how many unshared?
Two.
Okay, and minus 1/2 of shared electrons. And how many shared electrons I have for sulfur?
6.
6 of them are shared. So sulfur has 8 electrons, 2 of them is unshared and 6 of them are shared. So if I do this math, 6 minus 2 is 4 minus 3, right? It's going to be a +1. So I have formal charge for sulfur is going to be +1. So I have a +1 here. Did I do the math correct?
Yes. Yeah.
Okay. For oxygen 1 formal charge. How many valence electrons do I have? Oxygen is in group 6. So valence
6.
electron is 6. Minus oxygen 1 has how many unshared electrons?
4.
4. So this is unshared electron. And then this would be half shared. And this one is valence electrons. Valence electron minus unshared minus half shared. And how many shared electron I have for oxygen 1? 4. So half of 4. Okay. There's another way of saying this. You can say that valence electron minus unshared electron minus number of bonds. Number of bonds is actually half of the number of shared electron. But this formula is more, it has more background in it. So they use this formulas more. So the answer is going to be 0, right? If I do the math incorrectly, let me know because I don't want to. So oxygen 2, formal charge. What should be the formal charge for oxygen 2? Before calculating, I would say SO2 is neutral. Since oxygen 1 has 0, sulfur has a +1, oxygen 2 must be -1. Just before doing calculation, I can predict that, but I do the calculation for practice. 6 valence electron minus 6 unshared electron minus 1/2 of 2 shared electron, that gives me a -1. So the formal charge for oxygen 2 is -1. So -1 + 1 + 0, that is overall 0 charge for SO2. For the other structures, same thing, you can practice. We have solved problems in this PowerPoint for chlorine. Each chlorine has a formal charge. Iodine has a formal charge. The chlorines, they have formal charge of chlorine, I think is, if I box it out, I see like 7 electrons belong to this chlorine and 7 valence electrons, so the formal charge for chlorine would be 0. That's another way, and that depends on which book you are using. Sometimes you box it, you cut the shared electrons in half, and then these electrons belong to it. You see 7 electron, valence electron is 7, so it must be. Now for iodine, what I see here, I have 1, 2, 3, 4, 5, 6, 7, 8 electron, so it would be -1. And that -1, it shows outside of this bracket as the charge for the ion, or charge of the overall charge. Okay, so now that you had a couple examples, at least how to calculate the formal charge, and you have like different resonances. Here we have 3 different resonances. Formal charges have been calculated for the CO2, and we are trying to find out which CO2 is the best. Okay, which CO2 is the best? Which structure for the CO2 is the best? Which one is the best just by looking at 1, 2, 3? Which one is the best?
1.
One is the best, and that is the structure. Do they exist? Does it exist at this point? Yes, sometimes. Is a pi bond, it can move around, it can go to this. Overall charge is okay, but that's not good. And this is the worst one. Why is the worst one? Because oxygen is highly electronegative, and then you are giving a plus charge. That's not good. Okay. If there is a plus charge in the molecule, it's preferred to go to one with the low electronegativity. So we have the resonance structures. I draw the resonance structures for SO2 because I knew that I have the NO2 here. So the bond, you see that you have a single bond and double bond between oxygen 1 and oxygen 2. Okay, oxygen 1 has single bond in the structure A, in the structure B, oxygen 1 has double bond. So if you have two resonances here, and someone asks you, what is the bond order for the nitrogen oxygen 1? Well, half the time is single bond, the other half time is like a double bond. So overall, it's going to be 1.5. The bond order, when you have resonance, you can say two resonances, and then the total is going to be like one, between is switching between the pi bond is switching or is being shared between two other bonds. So this one always exists there, okay, always. And then the other one is shared between two, oxygen 1 and oxygen 2. So if it's shared between two, it would be 1.5 bond order. And if I say bond order, I prefer to say NO bond order, so more specific. They are identical. Each one is because it's not, you cannot take this as like the two of them together. It gives you the structure. And if you want to represent only as only one structure, you have to hybridize that. You would say hybrid resonance, and you would draw a single line like a solid, and then the pi bond you use like dash line, or you use dotted line. That means that it's sometimes here, sometimes there. So the resonance hybrid, this is the resonance hybrid. The two choices. Resonance hybrid, it could be this or the other one or two. You can draw both of them with the double arrow, or you can draw one and then show me where which bonds are being shared. Okay. Your questions regarding the resonance, did you get the formal charge? The lone pairs, you don't have to show for the domain elements. That's a good question. The only ones that you have to show is for the central atom, and you don't have to show for the domain elements. So you have to show it. If I didn't write it, that's not good. You write you draw the lone pairs for the central atom. The class is finished now. Okay. That was a question.